Hi, my name is Louis Lira, and welcome to my PowerPoint presentation on the practical design and use of PLC-based PID controls. I will be discussing the definition of proportional, integral, and derivative PID controls, as well as giving examples of the practical design and use of PLC based on PID controls in industry, and some advantages and disadvantages of proportional, integral, and derivative PID controls. PID control is a fundamental technique that is used in manufacturing and automation to maintain stable conditions. Whether you're adjusting temperature or pressure or speed, PID controls help keep those systems running smoothly and efficiently. Proportional control is a feedback method that automatically adjusts an output, like a valve or motor speed, in direct proportion to the size of the error between the target set point and actual process measurement. For integral control, it is a mechanism within a PLC that continuously accumulates system error over time and adjusts the output to eliminate long-term steady state errors. On the other hand, derivative control adjusts the control output based on the rate of change of the process error over time by predicting future errors based on how fast the measurement is moving. Some advantages and disadvantages of these controls include for proportional controls, advantages will be simplicity. It's the easiest feedback controller to implement, requiring minimal parameters to tune. Also, speed and stability. It reacts immediately to system errors and brings stability without causing excessive oscillations. Though some disadvantages would be steady state error or offset. It cannot completely eliminate the error in the system or persistent gap between the actual output and set points remains. Also, overshooting. Tuning for faster response times often results in the output exceeding the desired set point. For integral control, some advantages would be it eliminates steady state error. Unlike purely proportional controls, which often leaves a small gap between the target and the actual process variable, the integral function continuously adds up past errors to drive the process exactly to your set point. Another advantage is tunable for long-term precision or tuning for long-term precision. By adjusting the integral gain, you dictate how aggressively the PLC corrects prolonged deviations. Some disadvantages for this control would be sluggish response. Because the controller has to wait for an error to accumulate over time before making a large correction, a standalone integral system reacts slowly to sudden system changes. Another disadvantage is integral windup. If a process is physically blocked or requires a long time to reach the set point, the error keeps accumulating, driving the controller output to its maximum limit. When the process finally responds, the controller will severely overshoot its target and require time to unwind the accumulated error. For derivative control, our advantages are improved stability and speed. By counteracting rapid changes, derivative control increases system damping. This allows you to use a higher proportional gain, making the system respond faster with less overshoot. Another advantage is anticipatory action. This control system predicts future system behavior by looking at how fast the error is changing, allowing the controller to apply corrective action before the error becomes large. Now, some disadvantages would be high sensitivity to noise disruption. Derivative action calculates the slope of the error. If the feedback signal has electrical noise or rapid fluctuation, the derivative will amplify this noise, causing erratic and damaging output spikes to control elements, which is not good. It can also cause instability. If the derivative gain is set too high, it can overcorrect the system, leading to sustained oscillation and instability. Some examples of these controls include like temperature control in plastics and food processing companies. The heating elements, like those of an extruder barrel or an industrial oven, require highly stable temperatures to prevent material degradation or uneven curing. And flow rate and mixture controls, like chemicals and beverages. Chemical plants and bottle facilities need precise ratios of ingredients or steady flow rates through pipes to maintain chemical reactions or accurate product fill levels. Also, pressure regulation, like oil, gas, or compressed air. Uh, Gas pipelines and large-scale manufacturing air compressor systems must maintain specific pressure range to prevent equipment failure or explosive hazards. Liquid level control, like batch processing, like medicine manufacturing, uh, they have mixing vats and distillation columns or cooling tanks that need steady fluid levels to manage volumes and avoid overflow. Tension control and roll-to-roll manufacturing, like paper, textile, and film. In winding and unwinding materials like paper webs, plastic film, or sheet metal, the tension must remain perfectly constant. If the tension is too high, it snaps. Too low, and it tangles. Like, could you imagine rolling up a roll of toilet paper on your own? To be able to get the tension to be even throughout the whole roll would require so much like steadiness, steady hand, and it's just really hard for us to do as humans. But for a robot, when you calibrate it to a certain set point, it's a whole lot easier for a robot to be able to um, keep a steady tension rate than we can. So this is very important in these kind of industries. I couldn't even imagine trying to do something like that in a workplace without these kind of controls and robotics. In conclusion, without PID controls, industrial machines would be a lot less efficient and stable. A lot of fine-tuning would be needed to maintain steady processing. This means more manual intervention to keep things stable, meaning operators would have to make constant little tweaks, and overall, the process would take more time to manage, costing manufacturing companies to lose money.